An ideal transformer is a theoretical device that transfers electrical energy between circuits without energy loss. It consists of two induction coils wound around a common magnetic core, characterized by zero resistance and perfect magnetic coupling. The operation is based on Faraday's law. When an alternating voltage is applied to the primary coil, it creates a varying magnetic flux. This changing flux induces an electromotive force, or EMF, in both the primary and secondary windings. To derive the EMF equation, we define the instantaneous flux as phi equals max times the sine of omega t. Here, max is the peak magnetic flux and omega represents the angular frequency, which is 2 pi times the frequency. By substituting our flux equation into Faraday's law, we differentiate the sine function. This results in the instantaneous EMF, which is negative n times max times omega times the cosine of omega t. The maximum value of the induced EMF occurs when the cosine term is at its peak. Therefore, Emax equals n times max times 2 pi times the frequency, where f is the supply frequency in Hertz. In AC circuits, we use the root mean square, or RMS value, for practical calculations. We find the RMS voltage by dividing the maximum EMF by the square root of 2, which is approximately 1.414. After simplifying the constants, we arrive at the standard EMF equation, E equals 4.44 times frequency, times the number of turns, times the maximum flux. This formula applies to both the primary and secondary sides. For the primary winding, we use N1 turns to find E1. For the secondary winding, we use N2 turns to find E2. Note that the frequency and maximum flux remain constant for both sides in an ideal transformer. By dividing the two equations, we see that the EMF per turn is identical in both windings. This leads to the transformation ratio, K, where the ratio of voltages is directly proportional to the ratio of the number of turns. In a phasor diagram, the induced EMFs, E1 and E2, lag the magnetic flux by 90 degrees. This phase shift is a direct mathematical consequence of the differentiation of the sinusoidal flux. To summarize, the ideal transformer assumes zero winding resistance and no core losses. The EMF equation we derived allows engineers to calculate the necessary turns and flux density required for efficient power conversion. By substituting flux with the product of flux density and core area, we get the expanded EMF formula. This concludes our look at ideal transformer theory and derivation. Generated by Vision Solve AI.